Hey everyone, welcome today to this presentation. It's essentially a paper review on selfless sequential learning by Rahaf Al-Judi and et al. A collaboration between KU Leuven and Facebook AI. This was a paper that came out in 2019 in ICLR, and it's a continuation of the continual learning problem that I've been discussing in this channel. So let's start. Before I go in, based on feedback, I'm reducing the time that I take for these videos to hopefully between 10 to 15 minutes long. So I'm cutting down on the results section by a lot. Essentially, I want to give more time to the notions and ideas presented by the authors in the paper. And if you're interested, you can go ahead and read the results that's presented in the paper later. So continuing on our journey on the field of lifelong learning. So previously we saw about continual learning setup where we are concerned about the model's ability to learn a new task n, given that we have trained on previously n-1 tasks. And a common problem in this field, in this theme, is catastrophic forgetting, where a model that's been trained on previous n-1 tasks, we are concerned about how well the model remembers about those tasks, given that we are training on a new n task. And this problem has been one of the problems in this space. And here the authors want to tackle this problem. And the main takeaway from this paper is that for a given fixed neural network architecture, and so this is a space where you're not concerned about neural network architecture can add in more capacities, etc. Here, you consider a fixed neural network architecture, which is trained sequentially on multiple tasks. These models are less susceptible towards catastrophic forgetting if the learned representations are disentangled while also maintaining sparsity in the network. And here, sparsity is achieved by penalizing the total number of active neurons. It's very keen insights, and the notions come from a lot of inspiration from biological neural network models, just step into some of the ideas and words that the authors are talking about here, mainly disentangled representations, sparsity in the network, etc. I may do a separate video on this topic. It's a very, if you look at generally neural networks in the nature, like biological neural networks, sparse neural network architectures are preferred all the time, almost 90 to 95%. And generally the reason is that there's less interference between the inputs to the model, and more importantly, I think it's most of these architectures are highly resistant to noisy input, and also in general noise in their representations. And sparse networks in general also have efficient and compact representations compared to just fully connected networks. So I might do a separate video on this later on. And how is sparsity connected to disentanglement? So in this paper, the authors argue that you want to have sparsity while also having disentangled representations for your neural networks, and this helps in reducing catastrophic learning. So if you look at current fully connected neural networks, there's no intuition or any idea about sparsity. And in general, these neurons are free to learn entangled representations. And due to this, as we know, they are highly sensitive to input and noise, and they typically tend to overfit pretty fast, and they are not good at generalizations. So prior work has shown that these entangled representations in neural network are a key cause of catastrophic forgetting. And also, in general, if you look at overfitted models, they're highly correlated in terms of their representations. That is, overfitted models lead to entangled representations. And so a notion that the authors provide here is that you want to disentangle your representation so that they're less vulnerable to catastrophic interference. So this is you should always do this. But they also claim that just generally disentangling, which you could do by simply looking at your activations and just penalizing the correlations between them. So just doing this disentanglement is not useful in a continuous learning setup. You should do this along with sparsity inducing loss functions. So this is your main notion. And also just quickly touching about pruning and sparsity of networks. So here the authors are not really talking about sparsity in terms of like parameter sparsity. So one can achieve a sparser neural network architecture by just simply learning a representation and then pruning it, essentially removing all the dead neurons, and then reinitializing the model. And this creates a sparse network in terms of like the number of parameters used. But this is not the sparsity that the authors are concerned about. They are more concerned about sparser representation. So from the figure, a notion of what they're trying to say is, like, if you can train model 1 to have like a train model, the model, and then you prune it on task 1, and now you have the sparse model in terms of parameter sparsity. But while training on tasks 2, you get these entangled representations, and this is what the authors want to avoid. Essentially, they claim entangled representation causes catastrophic forgetting. So what they're talking about is more representation sparsity, where you train on task 1, you have sparse representations for task 1, and now when you train on task 2, you have sparse representations for task 2 using the same network, and there's no entangled representations. So I'm just jumping into how authors do this, understanding what they are actually claiming, like how they are implementing this is, I think, the most important thing for me. And essentially, it's nothing but a loss function. So just going to dive into how, like, the prior ideas that were there in the field. Previously, there is no sparsity induction, but essentially there was still a notion of the weights not changing over time. So let me just dive in here. So let's say you have tasks for a new task Tn. You essentially want to minimize the loss function for that particular task. So you want to minimize, say, the categorical cross entropy loss or classification task, or maybe a regression task, etc. So you want to minimize the loss function for that over m examples, the average loss over m examples. Here, m is the number of examples you have for the data set for training for task Tn. Now, previous method, essentially the elastic weight computation method from previously, I will add the paper details into the description. So here, the notion that they had was you want to penalize the weight changes too. So let's say you had a prior set of weights for task n-1. Now we are learning on task n. The weights that is changed should be minimal as much as possible. But simply doing this isn't going to be that useful. You want some notion of like elasticity to how much weights can change. So essentially, you learn a parameter, this parameter which tells you omega, that's going to tell you how important a particular weight k is. And based on that importance value, you're going to make sure you penalize changes to those weights more. And if the importance is less, then you're free to change those weights as much as you want. So this omega is essentially, you find out based on how important a particular weight is, essentially through the amount of gradient activations that it produces. So over all the examples, you essentially compute how much active that particular weight is, or how important it is in terms of contributing to the lower layers. So that's it. So this was the previous methods. And here the author essentially wants to add a notion of sparsity. So it's the same loss function, but now we have this added loss, and this loss is over all the layers, in the network, and you want to essentially make that particular hidden layer to be as sparse as possible in terms of representation. And how are you going to do this? So the simplest way is to essentially take pairwise for a particular, so the simplest way for let's say for a particular hidden layer, you look at the activation output for neuron I pairwise, the neurons I and J across all the neurons. You look at pairwise for all the examples, and you find which neurons are active when for a particular example. So, and you want to penalize it. So essentially, you're saying for a particular hidden layer, you don't want more than one neuron to be active for a particular layer for a particular example. So you're saying, hey, you learned this representation. I don't want any other neuron in the same layer to have the same representation for those particular problems. So yeah, as you can see, this is a really harsh loss function. Essentially, it's asking no neurons to be active at the same time. There should be only one neuron in a layer to be active. And so that's the catch one. You can't just implement that loss function as such and expect good results. So for the authors hypothesize that complex task, you need multiple active neurons in the same layer to learn a strong representation. So so they create a regularizer, the same loss function. They add a penalty on how closeness, based on closeness. So essentially, the first loss function we saw here, the second loss function, we have a Gaussian decay loss on how close those neurons are. So essentially, neurons that are close to each other, you want the penalty to be higher, and neurons that are farther away, you exponentially decay how much penalty you want to impose over that particular set of examples. And I don't, actually, this doesn't really make much sense to me. For one, this is all, the implementations are based off fully connected neural networks in the paper, and there is no closeness in fully connected networks. What do you mean by 1 and 2 in a fully connected network? Neuron 1 and neuron 2 is close. There's no inherent meaning of closeness in fully connected networks, but I would prefer something like random sampling for the layer and just keeping that. I'm not sure. This works apparently. So this is the loss function that they proposed, and that's what we're working with. So you have softness in your sparsity by making sure that you don't overly penalize neurons in the same layer. Again, we can't simply just implement that loss. We don't want to change neurons that have previously learned something of high importance. So you want to discount the amount of change that you do to them too. And to do this, the simplest way that you can do this is look at how important a neuron is. And you can do that by just looking at essentially the gradient of that particular ith neuron over all the examples. You look at the gradient for each and every example for that ith neuron in I. And now you sum it up and you say, oh, this gradient represents how much important that neuron is for the entire learning process. So I want to keep that. I don't want to change it for the new task. So now alpha I is again a discount that tells me how much I should not change those neurons. So finally, we come to the loss function, which is their proposed loss function, SLNID, which is which is sparsity inducing local neuron inhibiting discount and with discount. And actually, I need to go back and look into that. But SLNID, and essentially what you have is you have a discount for how important those set of neurons are to its change to. So you don't want to have 2 neurons which are, you don't want to change the values for neurons that are very important. So essentially that's that. So this is their sparsity inducing loss, and they add it to the other loss function that I described before, and that's it. And they get good results. I'm not going to go into results. As it is just one image from the paper. So this is on the CFAR and Tiny ImageNet data sets. So they divide the CFAR 100 data set into 10 different tasks, where each task consists of 10 classification problems. So CFAR 100 has 100 classes. So each 10 classes are a set of 10 tasks. And they found that overall, the test accuracies for using the SLNID loss function is higher 2% improvement over decov. And here decov is nothing but the simplistic idea of just decorrelating looking at the Frobenius norm of the decorrelation matrix, covariance matrix between for a particular hidden layer. So that's essentially what decov is. It's much better than decov. It's also much better than just L1 norm, and it's also much better than no normalization, which is just a ReLU network. And so that's it from me. I think I went slightly over. Might do more such papers. Let me know what your thoughts are. Thank you.